Multivariable calculus, single variable topics continued. This lesson is about work. So here's a little guy lifting a box, and so he's doing work. And he's doing it the right way. Notice he's lifting with his legs, not his back. That's what we should all do. So let's say the box weighs 15 pounds. Well, I could even lift that. If he lifts it 1 foot, that's a little bit of work. He lifts it another foot, that's more work. And if he lifted it up over his head, that would be even more work. And he's working against gravity. The work done in lifting an object depends on its weight and how far you lift it. So the equation for work is force times distance. So the work to lift 15 pounds 1 foot is 15 pounds times 1 foot, which is 15 foot-pounds. The work to lift 15 pounds 2 feet is 15 pounds times 2 feet, which is 30 foot-pounds. And yes, the unit for work is compound with a dash, in this case foot-pounds. Okay, so that's the work unit. Now let's say the box weighs 30 pounds. Well, then he's doing more work. If we double the weight but maintain the distance, we also double the work done. Okay, so there's what we had. Work to lift 30 pounds 1 foot is 30 pounds times 1 foot, or 30 foot-pounds. Work to lift 30 pounds 2 feet is 30 pounds times 2 feet, which is 60 foot-pounds. Now in the metric system, the basic units used are meters and kilograms, and force units are called newtons, whereas in the English system, force and weight are the same. In the metric system, they're not, because kilograms are actually mass, units of mass, which just happen to be the same as weight on Earth, whereas weight takes into consideration mass and the force of gravity. So force units have a different name. They're called newtons. 1 newton is the force needed to lift an object that weighs 1 kilogram 1 meter off the floor. So more precisely, 1 newton equals 1 kilogram per meter per second squared. In other words, we're accelerating a kilogram 1 meter. And you could do that in space as well as on the Earth. Now work is measured in Newton meters then, more commonly called joules. So we got a lot of new vocabulary here that you have to get used to. So Newton meters are only going to be valid and called joules if your measurements happen to be in kilograms and meters. If not, then you're going to have to do some conversions. Work done with 100 newtons of force for 20 meters equals 100 newtons times 20 meters, or 2,000 Newton meters, which are more commonly called joules, 2,000 joules. Okay, and you'll see more of this in the exercises. So here's a little guy pushing a box along the floor, a 100-pound box. He'd have a hard time lifting it, but it's pretty easy to push. Now you've probably noticed that it takes a lot less force to slide a heavy box than to lift it, and therefore less work will be done. The work done sliding a box still depends on its weight and how far you slide it. However, it also depends upon the type of surface it's sitting on. So if you got a smooth, wax surface, it's going to be easier than if you're trying to push it along concrete. And then, of course, if you got a heavier box, it's going to be harder. It's going to be more work. Again, if you double the weight or the distance, the work will double. And if you double both the weight and the distance, then your work's going to quadruple. So work again does equal force times distance, always, always, always. This time the force used is working against the friction created by the weight of the object and the surface. So work to slide 100 pounds 3 feet is still 100 pounds times 3 feet, but it's also times mu, where mu is called the coefficient of friction and varies with the surface that the object is sitting on. Now here we have our worker man, and he's going to push an object up an inclined plane. So now he's got to work against gravity and friction, sort of a combination. Here he goes. Pushing an object up an inclined plane involves the forces of gravity and friction. These problems involve trigonometry and or vectors, not the calculus in this particular section. So we're just going to move on. We're only going to basically look at two types of problems. One is just going to be lifting things, and then the other is going to be about extending and pushing on springs. That's about all we're going to do in this section. Now, what if the force varies? For example, let's say we have a spring. If I push the spring in a little bit, it'll take some force. But now that it's compressed a little bit, the resistance is more, and it's going to take more force. So when I compress it even more force. And so the shorter it gets, the more I have compressed it, then the greater force is necessary. The same thing will happen if I stretch it. The more I stretch it, the more force I'm going to need to stretch it the same amount of distance. So Hooke's law says that the force necessary to compress or stretch a spring is equal to kx, where x is a displacement of the right end from the spring's natural length. So for example, if it started out at 4 inches and I pushed it to 3 inches, then x would be 1. If I pushed it to 2 inches long, then x would be 2. If I made it 1 inch long, then x is 3, etc. And so my force is varying as x varies. K is called the spring constant, and that will vary depending on the material the spring is made out of and how thick it is, and so on and so forth. Now, the distance, delta x, is the ending position minus the initial position. That's the total distance you're pushing it, and that would be the extra thing that you need if you're going to compute work. So, work is still force times distance. So you've got a varying force, and then you're going a certain distance. So you can't, put in 3 numbers and be done with it. So we could approximate the work by taking little increments. K stays the same, but x is going to vary, and then the change in x is going to vary. You're going to take little increments of, a quarter of an inch, and then another quarter of an inch, and another quarter of an inch, and so on. But that will just be an approximation. But if you look at it closely, you'll realize that's a Riemann sum. And so if you want the exact amount of work, all you've got to do is change it into an integral. If we depress or stretch the spring b units from its natural position, then here's our integral. Work will equal the integral from 0 to b, kx dx. K stays the same, x is now varying, and the little incremental changes in x become the instantaneous change in x. So here's an example. A spring has a natural length of 1 meter, and a force of 10 newtons is required to hold it stretched to a total length of 2 meters. How much work is done in compressing the spring from its natural length to a length of 60 centimeters, which, by the way, is 0.6 meters. You got to keep all your units the same if you want to get the right answer. You got to watch out for that. All right, so here's a little spring. Hooke's law says force equals K times X. And so since it took 10 newtons of force to do a distance X of 1, then obviously K is 10, right? So now the work, notice that we're going from 0 to 0.4. Why is that? Well, if we push it from 100 centimeters to 60 centimeters, then we've compressed it. The part we've pushed in is 40 centimeters, or 0.4 meters. So that's the reason we're going 0 to 0.4. And so we're going to integrate the force to get the work, 10x dx, and that's an easy integral. We have to, so that's 5x squared for the antiderivative, evaluated from 0 to 0.4, and we get 0.8 what? Newton meters, which are known as joules. Okay, so there you have an example. Let's look at another one. A spring has a natural length of 10 feet, and the work done to compress it from 9 to 8 feet is 30 foot-pounds. How much work is done in stretching it from 12 feet to 15 feet? Now notice there's a lot of different numbers here. Its natural length is 10, and our final question is it's already been stretched to 12. We only want to know the work to stretch it 3 more feet. Okay, so you have to think about what numbers you're going to use. Now this time, it's the work done, okay, that's 30 foot-pounds. Notice now we're in the English system. Work, not force. So, and we're compressing it from 9 to 8 feet, and its natural length is 10. So what are we actually doing here? Well, we're going from 1 foot of compression to 2 feet of compression. You see? 10 minus 9 is 1, 10 minus 8 is 2. And it's the work, the integral, that equals the 30 foot-pounds. So we solve the integral. We get 1/2 kx squared from 1 to 2 equals 30. You plug in 2 squared is 4, minus 1 is 3, times 1/2 is 3/2, and so k is 20. And now the next integral, we put 20 in for k, and we're going from 12 feet to 15 feet, so that's 2 feet past its natural length to 5 feet past its natural length. So our integral goes from 2 to 5. 20x dx, integrate, get 10x squared, evaluate, and we get 210 foot-pounds for this problem. Okay, so you got to read these problems carefully. Make sure what they're asking for is the equation that you're using is appropriate. Okay, now there are other situations where the necessary force varies besides compressing and stretching springs. For example, you could be hauling a leaky bucket up a well so that the weight is going to decrease as you pull it up, and so you're going to need less and less force as you pull. Or you could have a ball and chain on this crane vehicle, and as you lower it, you've got more chain, and the chain's heavy, and so the force is going to be greater. The pull of gravity on the ball and chain is going to be greater, and if you pull it upward, then again, like the leaky bucket, you're gonna need less and less force as you pull it upward because there's less chain. So we're going to take a look at a couple of examples along those lines now. A bucket weighing 5 pounds is full of water weighing 15 pounds when it is 10 feet down in a well. Eric lifts it to the top of the well at the rate of 2 feet per second. Also, the bucket is leaking at the rate of 1/2 pound per second. How much work did Eric do? Yow. Okay, well, let's get all these numbers straight. Here's a picture of the bucket. Now, what I'm going to do is have ground level be at 0 at the, because that just makes things a little easier. And there's the bucket halfway up. So it doesn't weigh quite as much as it did at the bottom because when it was 10 feet down in the well, it weighed 15 pounds, but as it moves up, the weight varies, and so, you know, your computation is going to have to be calculus. All right, so 10 divided by 2 is 5 seconds because it was 10 feet down the well. He pulled it up at 2 feet per second, and so it takes 5 seconds to reach the top. Now, why is that important? Because I need to know how much water is leaking out total. So 15 minus 5 times 1/2 pound per that second means that when you get to the top, it's going to weigh 12.5 pounds. So at any point in between, how much is it going to weigh? So every second, i.e. every 2 feet, we lose 1/2 pound of water, or 1/4 pound each foot. So at any position, y, which is negative in my picture, the weight, which equals the force in English system, weight and force are the same, is going to be 5 for the bucket, that doesn't change, plus 12.5, which is how much it weighs at the top at 0, when y is 0. And then since y is negative, I'm actually adding 1/4 pound for each y that we move up because y is negative, and so that's going to make it, for example, when you're down at negative 10, then you're going to be adding 2.5 pounds to get the 15 pounds. And then when you're up at the top 0, you're at your 17.5, which is the bucket plus the water. Okay? You might have to think about these and play with it a little bit. Don't think you're going to get them real fast, but that's how you have to analyze it. Okay, now the distance traveled is the change in y. So at any particular moment, it's dy. So here's my integral. I'm going to start at negative 10 and go all the way up to 0 on my integral. That's how far I'm going. That's the change in y. It goes from negative 10 to 0. And then the weight, which is also the force at any particular moment, is 17.5 minus 0.25y. And so this is the easy part. Calculus is the easy part. Figuring out how to set it up takes a little bit of thought. So here's my antiderivative, evaluated from negative 10 to 0, and I get 375 over 2 foot-pounds of work that Eric did. Okay, so there's the leaky bucket, and again, see here, the work is we're just working against gravity. We're just lifting, but in this case, what we're lifting is varying. Okay, another example. A building demolisher consists of a 2,000-pound ball attached to a crane by a 100-foot chain that weighs 3 pounds per foot. At night, the chain is wound upward and the ball is secured 100 feet above the ground. How much work is done by gravity on the ball and chain when it is lowered to the ground in the morning? Okay, so now the weight is going to vary depending on how much chain is being lowered. You know, like when the ball starts out, it's just the ball, and then as it comes down, there's more and more chain, and so the weight is going to vary again, just like the last example. Only this time it's getting heavier instead of lighter. Okay, so here's my picture. It's attached 100 feet, and this is the picture of the ball part way down, you know, on its journey to the bottom. And there's going to be 100 minus y feet of chain at each spot y along the journey down the y-axis. And then the ball's going to weigh 2,000 pounds. So the weight is going to be 2,000 pounds plus 100 minus y feet times 3 pounds per foot. So we're going to integrate. Now notice I'm starting at 100 and going to 0. We're going to talk about the ramifications of that in a minute. And so we've got our 2,000 pound ball plus the length of chain times 3 pounds. Okay, so I don't like that 100 to 0, so I'm going to take the opposite of the integrand and switch the limits of integration and then do a little arithmetic there. Okay, so instead of minus 3y, we got plus 3y. And instead of 2,300, we've got minus 2,300. All right, so now the calculus part's easy. Integrate, evaluate, and we get a negative answer. Now, why is it coming out negative? Well, because gravity is working downward. The work is in the negative direction along the y-axis. So mathematically, it should come out negative. The answer comes out negative because the force of gravity pulls downward, which is in the negative direction along the y-axis. So when you answer it, you wouldn't put a negative in your English answer. You would say gravity does 215,000 foot-pounds of work lowering the ball. All right, so we've seen examples where the weight or the force varies. Now we're going to look at an example where the distances vary. In some situations, different portions of what's being lifted travel different total distances. For example, pumping a liquid out of a tank. If you've got liquid near the top, for example, if it's water, water near the top will travel a shorter distance if you're pumping it up over the top than, say, water way down below the ground near the bottom of the tank. And so if you're going to pump all the water out, you've got varying distances among the different levels of water. Number 10. A cylindrical tank with radius 5 feet and height 10 feet rests on the ground with its axis vertical. How much work is done to fill the tank with water from the ground level? Okay, so here's my picture of the tank. Ground level is going to be the x-axis. And you can think of the water as being pushed up into the cylinder in slabs, cylindrical slabs. And each slab has a different distance to go. This one's kind of in the middle, so it would go up, say, 5 feet. And then there'd be a slab that goes all the way up to the top, and one to 8 feet, and one to 7 feet, and so on and so forth. So the force needed to move the cylindrical slab of water from the ground up into its position is its volume, the amount of water, times the density, which is the weight of the water per unit. And to get the volume, you need the area of the top of the slab, which in this case is circular, which would be pi r squared. And that's always going to be pi times 5 squared. That's not varying. And then the depth of the slab, or the height of this little cylinder, would be the change in y. So it's 5 squared, pi r squared is 25 pi, and that's in feet squared. And then you've got the height of the cylinder, which is delta y, and that's in feet. And then you've got the weight, the density of the water, which happens to be 62.4 pounds per cubic foot. And so you'll notice that the feet cancel, right? So we end up with 25 pi times change in y times 62.4 pounds. Okay, now we have to figure out the distance each slab travels. And that's just going to be y feet, because the bottom one travels no feet, the top one travels 10 feet, and everything in between travels the y value on the y-axis. And so there's your feet back, okay, because you've got pounds and now you've got feet, so you're going to end up with foot-pounds. So the work is the integral from 0 to 10 of 25 pi times 62.4 y is a distance, and then delta y turns into dy because now we're having infinitely thin slabs traveling up, instantaneous change in y rather than delta y. Notice that the limits of integration are from 0 to 10 because that's where the liquid's going to end up on the y-axis. Bottom at 0, top at 10. So now the setup then is the hard part. The integral is simple. Integrate, evaluate, and we end up with 78,000 pi foot-pounds. Number 16, a cylindrical tank full of gasoline with diameter 6 feet and height 10 feet is buried on its side with its highest part 5 feet underground. How much work is done to empty the tank into cars whose gas tank openings are 2 feet above ground? The density of the gasoline is 45 pounds per cubic foot. That's what we're going to use anyway. So here's our picture. Notice that the tank is sideways, so 10 runs parallel to the x-axis, and the top is at negative 5 feet underground on the y-axis, and then the bottom then, since the diameter is 6, is going to be down at negative 11. And then there's a 2 up there where we're going to pump all the water out. So the difference here is the last one, we were pumping the water in, and this one we're pumping the water out. But the way we do it is exactly the same. So here's a slab of water somewhere in the middle of the tank, and this time it's a rectangular prism. And so the top of that prism is going to be length times width. The length is always 10, but the width is going to vary depending on which part of the circle we're at. So what we need, we're going to need an equation of that circle. So to do that, I create another axis, which would be the z-axis, but I'm going to call it the w-axis for width. And that means that the area of that slab then is going to be 2w times 10. So the force necessary is going to be the volume times the density, and the volume is going to be 10 length times 2w, which is the width, times the depth of the slab, which is the change in y, times the density, which is 45. But now we have a little problem because we've got to get w in terms of y before we can integrate. So let's talk about the equation of that circle on the wy plane. The center is at 0 on my w-axis because that's the way I drew it, and it's at negative 8 on the y-axis. And the radius of that circle is 3 because the diameter is 6, so half of 6 is 3. So our equation is y minus negative 8 squared plus w squared. So at this point then we can solve for w, and w is going to be the square root of 9 minus the quantity y plus 8 squared. Now the distance each slab travels is going to vary. The very bottom slab is traveling from negative 11 to 2, which would be 13, and then at the top slab is only traveling up 7 units. And so somewhere in the middle, how far is it going to travel? Well, it's going to travel up whatever the y value is, only opposite of y because y is negative. So the distance the slab travels is going to be negative y, and then plus another 2 feet to get up to the cars, which are 2 feet above the ground. The work then is the integral from negative 11 to negative 5, 10 times 2w times 45 times the distance 2 minus y, dy, for the delta y turns into dy, and then notice that I didn't bother to do that one by hand. That would be pretty hefty. Probably could be done, but I just typed it into my calculator and got the answer of approximately 127,234.503 foot-pounds. So now before we stop, let's consider a general integral for pumping liquids, because these problems tend to be a little trickier, so I just want to review what we're doing here. First of all, your limits of integration start at the bottom position of a liquid and end at the top position of a liquid. Now, if you're pumping out of a container, then these are the positions at the beginning of the problem. If you're pumping into a container, then these are the positions of the liquid after you've finished pumping. But it's still the numbers on the container where the liquid either begins or ends up. And your integrand then is the density times the area of a cross section, and then the dy combines with the area to make volume, and that combines with the density to make the weight or the force, and then the distance each slab of liquid travels is the distance. And so you should have these four things in your integrand. Now let's review the limits of integration with a couple of examples, because students tend to have trouble with that. Here's a cylindrical tank sitting on the x-axis. Where is the liquid? What would your limits of integration be? Did you say 0 to 3? If so, you're right. How about this one? Did you say -8 to 0? Then you were right. And remember, this could be a picture of after you've pumped the liquid in, or it could be a before picture before you pump the liquid out. Okay, so now I leave you with a beautiful picture of a waterfall and gravity doing work, pulling the water over the rocks. Have fun as you do these problems, and don't work too hard. Whoa.
I've been working on my calculus all the livelong day, and I found the hardest problems to ever come my way involve the work of pumping liquids and stretching springs out too. But quitters never win and winners never quit, so I figured out what to do. Work equals force times distance, but force and distance vary. That's what makes the integral an absolute necessity. Force needed to stretch a spring from its natural length equals K times X, and when you integrate that you get work. K is a special constant. X is how far you stretch it. Limits are the incremental differences which the start and stop position suggest. I've been working on my calculus all the livelong day, and I found the hardest problems to ever come my way involve the work of pumping liquids and stretching springs out too. But quitters never win and winners never quit, so I figured out what to do. Pumping liquids is complex. You need weight per unit times the area times the distance times the thickness, which is just dx. In the metric system, instead of weight, you'll need a mass per unit called density times the constant of gravity. There are several other applications like buckets and cables and ropes, but the fundamental thing you need to know is that work is the integral of force. I've been working on my calculus all the livelong